All right, so welcome to the course on machine learning for chemical engineering. This is the first lecture, and here we'll be talking about the general outline for the course, as well as some preliminary definitions about machine learning and different classifications and so on. So to start with, just briefly, my name is Antonio del Rio Chanona. I am a faculty at Imperial College London, and my group focuses on research on optimization and machine learning applied to process systems engineering. Now, the idea is that this course, you will learn about machine learning and data science and how this can be applied to general engineering, but also specifically to chemical engineering. Now, throughout the course, we'll be looking at many different types of machine learning, algorithms, methods, and so on. And throughout, we'll have some further study material in case you want to dive deeper into some specific parts of the course. So briefly, let's go through what will you learn throughout the course. So we've structured the course into these 5 different sections. So the first one is very brief. That's basically all we need today. So what is machine learning? Then we'll be going through different machine learning models. Then how you can use machine learning for things like fault detection or anomaly detection. Then going into what we call data-driven optimization. And finally, on how you can apply machine learning into dynamic systems and control them, such as reinforcement learning, maybe to play games, but also using data-driven control to, for example, control reactions or reactors and supply chains and this kind of things. Now, this overlaps very nicely with how machine learning courseworks are laid out. So we have supervised learning, which is basically, again, how you build machine learning models from data. Then we have unsupervised learning, which is how you allow patterns to be discovered and how this can be used for fault detection and anomaly detection. Then there's this part on Bayesian optimization and derivative-free optimization, which again nicely overlaps with data-driven optimization. And finally, the last part is again reinforcement learning, time series prediction, which is reinforcement learning and data-driven control. We have an extra lecture on large language models, of course, because they're very interesting and important right now. But that's a bit outside of this. But we'll be talking about this as well. Okay, so a typical first question is, there's a lot of buzzwords going around. So what is the difference between machine learning and artificial intelligence? And I just generally like to set the scene on these two different topics. So the first one, and I'm going to speak broadly here, right? I'm going to make a few simplifications here, but artificial intelligence is more about the overarching goal of creating machines that simulate human-like intelligence. This goes into human cognition, reasoning, and for this, you have to delve into things like neuroscience. Now, instead, what we're going to be looking at is machine learning, which is a subset of AI, which is focusing on developing the algorithms and applying these methodologies so that machines or computers can learn from examples and then without being explicitly programmed to do so. And we'll be talking about exactly what do I mean by this. And this course focuses on this part, more on the machine learning part, the algorithms and the methodologies that can be applied to engineering. So, having said that, what is machine learning? So, I always like to start describing what is machine learning through an example. So, let me take you back. And traditional computer science, or even what was called machine learning earlier, is how we could get computers to do tasks by giving them very specific instructions. But obviously, computers can do things faster, do simulations internally. And this was the era of what we could call expert systems. So the idea here is that some engineers would know very clear domain knowledge, and they would give very clear instructions to a computer on what to do. I'm obviously going to do many oversimplifications, but the big picture idea is, for example, if you wanted a computer to learn how to play chess, what you would do is you would hard code different instructions to the computer. So the one that I have here is, for example, given a board configuration, the computer would know that if the opponent moves the horse to some position, then you would move the bishop to protect yourself. Otherwise, you would move the queen, maybe to attack. Yeah, and again, this was based on expert knowledge that the engineers would talk to professional chess players, and they would very clearly give instructions to computer players. Again, now oversimplifying, generally there were some simulations internally that the computer would do to outline different strategies and see which ones had the highest probability of winning the game. But that's a big picture idea. It's called expert systems because you would get information from experts and you would give very clear instructions to the computer. An example that we'll be seeing, and again, this is once again as oversimplification, how would traditional computer science learn to classify cats and dogs? Well, you would have an algorithm that would look to specific features, let's say the snout, which in generally in dogs is a bit more pointy. So you would say, well, if the snout is pointy and maybe the animal that's in there is big compared to what's around it, then it's a dog. And otherwise, it would be a cat. Yeah, and again, here you would very clearly tell the computer what to look for so that it would make a decision. And this is what we would call traditional computer science. Now, if you want to go more into the new and modern machine learning, the idea is that here we provide examples. So we provide examples of what are cats, what are dogs, and then we expect that when we give a new picture of a cat or a dog, then the computer would be able to, based on the training data that it got, it would be able to on its own extract the features and be able to tell you if it's a cat or a dog. So basically machine learning would accomplish tasks based on examples. Following this, there is a very nice definition, which I like, from Arthur Samuel. If you see, it's actually not particularly new, but the definition that he gave was that machine learning was a field of study that gives computers the ability to learn without being explicitly programmed to do so. Yeah, and this is what we will be talking about, and I'll go through some examples of this. Okay, so again, with the theme of what is machine learning, generally we divide machine learning into three different parts: supervised learning, unsupervised learning, and reinforcement learning. And today I'll be going briefly through each of these, and throughout the course we'll be looking at them in more details, including the methods and the algorithms. So supervised learning from machine learning. Okay, so here, why do we call it supervised learning? Well, we call it supervised learning because we provide the right answers. So following the example of the cats and dogs, we have an input. In this case, the input is the picture of a dog or the picture of a cat, and we provide the output or the right answer. So in this case, we say this is a dog or this is a cat. And what we hope is that by giving many examples, the computer is able to generalize and to, given a new picture, tell us this is a dog or this is a cat. So with a bit more pictorial example, let's assume that you wanted to classify points which were either green or red, and this was variable 1 and variable 2. And you would give many examples, right? So for example, if you say, okay, given that variable 2 has this value and variable 1 has this value, then your point is going to be green. And you would do this for a few points. So here, like you say, green and red. And then what the computer would do or would learn is a mapping that looks like this one over here, where then a new point, if it was maybe this value variable 2 and this variable 1, it would say, okay, it's probably a green point. Now, this is a very clear distinction where I don't have some points, because it can happen that maybe I have a red point over here, and sometimes this can be misclassified. And that will, in real examples, that can happen. But the idea is to try to create the best contour that best classifies from these different colors. Yeah, so we'll be looking at more examples of this, but that's the main idea, that you're able to, based on examples, classify something. And this is what we would call supervised learning, again, because we're giving the right answer. So at the same time, so we have supervised learning, and in machine learning, generally we divide this into classification and regression. So classification is what you would expect, where you classify. So the examples of cats and dogs, again, the input was an image. We would give the correct answer for what we call the training set, and we would give many pictures of dogs, many pictures of cats, and we would say these are dogs, these are cats. And then when a new picture comes up, we would expect the machine to be able to distinguish this is either a dog or a cat. Again, we call that classification. In the same way, we could have a different example where now the input is not a picture, but it's an age and a tumor size, for example, for medical applications. And here we would be able to check if a tumor was benign or to predict, or if it was malignant. And as you can see here, we would initially have some data. And the idea here is that, okay, what happens if a new patient comes in and now the tumor size of the patient looks like this and the age looks like this? Is this likely to be benign, or malignant. The idea is that providing many examples, a machine learning algorithm would be able to say, well, in general, this would be the line that we would be able to draw, and this tumor is likely to be benign. Now, as you can see, there are some examples. So, for example, this is malignant, and it's on this side, and this is benign. There are some examples that would be misclassified, and these would depend on your application. In this case, what would happen is that this would be an initial screening to see which are the patients that are more urgent to see, because they're more likely to have a malignant tumor. Also, of course, this is in 2 dimensions, so it's very easy to see, but when this is in many dimensions and you have many correlations, it's good to use an algorithm rather than a human eye. And again, this is the main idea of classification, where you give some inputs. It can be either pictures and classifying between cats and dogs. It can be just features, like this is the age, this is the tumor size, and classifying as well. So this is the first type of supervised learning. Now, the second type of supervised learning is what we call regression. And the idea here is that you're not predicting between different classes. That's classification. The idea is you're predicting a continuous value. So this is an example where you have the size of a house, for example, in square feet, and given a training set. So again, you go out, you collect different houses prices and square feet of those houses. You plot them, let's say, or you collect the data, and then what you do is you try to find the function that describes, given a new house, for example, 750 square feet, what is the likely price that it would have? Well, then you would be able to look at this line and show it. So again, this is a second type of supervised learning. So we have classifications, which generally sort things into different classes, and we have regression, where the idea is that you are going to predict a continuous value and say, for example, given the size of a house, what is the price? Okay, so that is the general outline for supervised learning. Again, the idea is that you feed the learning agent with examples and you hope that it generalizes. And this generalization is in the form of fitting some curve to the data. So that is what at least I like to say, or I like to think about it as general problem of regression. So again, although supervised learning can be classified into classification and regression. Classification, distinguish between different classes. Regression, try to fit a curve and output a continuous value. In general, both of these cases, we're fitting some type of line, so both of these cases are some type of regression. I hope this is not too confusing. We'll actually be looking at this as we go along throughout the course. So some more specific examples. Let's start with the one that we saw before. So you have, for example, a neural network, which is the typical machine learning example. And what you would do is you would feed images of cats and dogs, and you would tell it, these are cats, these are dogs. And the idea is that once you get a new example, a new dog in this case, the neural network is able to tell you, well, with some probability, this is a cat, with some probability, this is a dog. And again, this is what we would call classification, because we make Boolean decisions and we sort whatever input we get into a class. Again, this doesn't have to be an image necessarily. Here it is. But it can be something like the example that we had before for the tumor size and the age of a patient. Now, the other example that we try to look at is regression. So now a bit more complicated. So again, what you could do is you could feed in square meters or feet, depending on where you are, postcode, number of windows, and that would probably give you, given a lot of data, so we're assuming that we have a lot of data, we're able to train this model, and then when a new house comes up, and we know the square meters, the postcode, and the number of windows, then we could say, okay, this is the likely value of the house. And again, this is what we would generally call regression, because it predicts continuous values. So now going into a more chemical or science example, we could do this with many other things. And this is one of a typical thing that is right now done, and is very hot, doing it for pharmaceutical industry. So for example, we have many molecules that help us create better drugs, better medicine. and we already know of many of these molecules and what are the properties. So what we can do is we can grab all the molecules that we already know about the properties, we can feed them into a neural network, and we can tell them to try to learn the type of these kind of properties. Now, in general, these properties, again, will allow us to have some specific behavior that are good for some specific medicinal purposes or other types of applications. However, every molecule, so trying out every molecule in the lab, for example, maybe takes 2 weeks. And trying every molecule, maybe even in a quantum mechanical calculation, which is an approximation of what would happen in the lab, maybe that would take us maybe a few hours, maybe up to a day, because you have many very expensive calculations to do. However, if you want to scale billions of molecules or millions of molecules, you cannot really do that. So what now people are trying to do, and again, I'm oversimplifying this, is that they train neural networks based on the properties that we already know that some molecules have, and then they're able to predict the new properties of new molecules and screen which are the most likely to have the properties that we want to have. And then those are either tested in quantum mechanical calculations, probably, and then the number is further reduced to have a few tests in the lab. And that's a general typical workflow right now that allows for discovering new drugs or new molecules that are useful to us. Now, the idea here is that the neural network, in the end, acts as a model, acts like we would call a lower fidelity model, to, for example, density function theory calculations or models. So DFT is a type of quantum mechanical calculations, and this is what we generally do. So instead of having a machine learning model, people, very experienced and smart people, actually put together models based on physics and chemistry, and these are DFT models. Now, instead of that, what we could do is we could have a data-driven model, in this case, for example, for predicting the properties. Now, depending on the type of model, generally, these models will be maybe less effective or less accurate, like machine learning models. They're getting actually to a point where they're very, very accurate, but they take much, much less time. And if you have a lot of data, so in the pharma industry, sometimes we have a lot of data, then it can actually be very useful and they can be very, very accurate, sometimes even more than density functional theorem or quantum mechanical calculation models. Yeah, but anyway, this is a way in which we can actually use machine learning and in a supervised way. Now, another example is, let's assume that you have a chemical reactor and you have a few experiments where you give, maybe you have a temperature condition, maybe you have a pressure condition, and maybe you have maybe some specific catalyst. And then given these operating conditions of how you operate in your reactor, you can predict how much conversion or how much production you have of a specific reactant or molecule of interest. And you could do this for many different types of conditions and measure how much yield you get. And then in the end, you can use this as a model for your reactor. Now, I need to say here that you should not always use machine learning, and actually machine learning is a solution to very few of our problems. Most of the time, for example, if you already have a very good model of your reactor, you should probably use your very good model of your reactor, because we know a lot, like we engineers know a lot about the physics, the chemistry, and we can actually model this very accurately, and then just use a few experiments to calibrate our models. Yeah. So what I'm saying here is that while you could do this with machine learning, and I'm putting this just as an example of what you could do, it doesn't mean that you always should use it. And most of the time, if you have accurate models based on physics and chemistry, you should probably use it. There's also this new trend of research, which is physics-informed machine learning, which basically means if you have some domain knowledge, you should use it and put it inside your model. And in some cases, that works very well, but in general, if you have a very good model based on physics and chemistry, you should use that instead. Okay. All right. So that was, again, what supervised learning was, a bit more in a whirlwind. Again, the idea here is that you have examples where you have it's a regression problem where you have some input and its output, the correct answer. And based on examples, you allow the machine learning model to learn about this, so that when you provide a new example, it can give you a prediction or an approximation. And again, we'll be seeing a lot about this and these types of models that we can use here later throughout the course. The second type is unsupervised learning. And why do we call it unsupervised? Well, in the supervised learning, you would provide labels, or you would provide the right and the wrong answer. Either you would provide what is the price of a house, or you would provide this is a picture or of a dog or of a cat. In this case, what you do is you only give inputs, and you hope or you use algorithms to be able to identify patterns of groups. Now, all machine learning is what we would call pattern recognition anyway, but intuitively here you can say it more broadly, that you give input data and you allow the algorithm to find specific patterns. Now the picture here that I mean, for example, this is the one that we talked about on supervised learning. Now when we have unsupervised learning, you can think of it, so you only give points, like here, you only give points, but you don't give any color. And what you do is you ask the algorithm to find clusters. So in this case, you could say, well, can you find points that are very close together and at the same time they are farther away from other points? You can see that these points are all close together and they're far away from the other points. These are all close together and they're farther away from the other points. There's obviously many questions here. How many clusters do you want? Is it better to have 2 big clusters, or in this case 4 or 5 smaller clusters? And these are questions that we will be asking and answering hopefully throughout the rest of the course. Now again, this is the first type of algorithm, clustering. So this is a very typical example. Again, this is a 2-dimensional case. This is a 3-dimensional case. But of course, here you could probably do it with your eyeball. But if you're looking in high dimensions, what you actually want is to be able to have an algorithm that could find this in 100 dimensions or in 50 dimensions. Another very typical example on unsupervised learning is community detection. So this is similar to clustering, but done on networks or graphs. So this is something that, for example, Facebook used to do very much before. I'm not sure if they keep doing that. But let's assume that this was your social network of your group of friends. And if 2 friends of yours were also friends between them, they would have an edge between them. So maybe Facebook would be able to say, okay, this is probably your group of friends from football, because maybe you also have in the chat that ball or match gets mentioned a lot. Maybe you have another group of friends who are also friends amongst them, but then in this case there's a lot of words like assignment or homework, so this is probably your school group of friends, and so on. And again, here you would only provide the network, and then the algorithm is able to detect automatically, obviously using algorithms, these different communities, and that's why it's called community detection. Then there's finally dimensionality reduction. There's other types of methods, but these are the 3 that we're going to be looking at for now. And for example, it's when you have some data in a very high dimension, but you can actually reduce the dimensionality so you can analyze or visualize it better. So in this case, I'm saying I have a 3-dimensional data, but actually it could be done in only 2 dimensions without losing too much of that information. And maybe even that could be further reduced into 1 dimension without reducing too much of the information, or not losing too much of the information. Okay, so that was unsupervised learning. And now we're going to the last type of machine learning, which is reinforcement learning. Now, the idea of reinforcement learning, and maybe you can think about this, comes from the name, comes from animal psychology, where we train our pets by reinforcing good behavior, by giving them treats, and discouraging bad behavior in any way, maybe not giving them treats. And the idea is that we could do something similar with computers, where we would give some type of positive reward. We'll talk about throughout the course what this means. For example, for the computer winning a game, if we're trying to have a computer that learns itself to play a game, and give a negative reward for doing bad, let's say losing a game. So the best way that we can do this is with an example. So some time ago, depending on what you think, this was in 1996, there was this big match between Garry Kasparov and Deep Blue, which was a computer from IBM. And the idea here was to see who was the better player, the best human in the world versus the best computer in the world. The idea here is that Deep Blue, so this computer, was programmed by IBM engineers in the traditional way, or what I call the traditional way, which was the expert systems. So again, I'm doing many simplifications here, but IBM engineers they talked to professional chess players, and they would program the computer based on expert knowledge. And this would tell Deep Blue how to play the game. Obviously, Deep Blue could do many it would try to simulate games internally before making a move to see which move have the better probability of winning the game. But this was the idea, that it was expert system because it was all if-else loops, where IBM engineers would program very specific instructions for Deep Blue to try to play the game. Now, the final score, it was 1-1, a bit disappointing. So, the best human in the world and the best computer in the world were evenly matched. And then the question is here, can computers do better? And now we fast forward to 2016. There's this new supercomputer called AlphaGo from Google DeepMind that is playing the game of Go. Now, Go, without going into too many details, is this game which is more complex than chess, and it has what we call a broader search phase, which means that you can have many more moves that lead to many more different outcomes of the game. It's also a bit of a more abstract game. So in chess, for those of you who know how to play this, you're basically taking out pieces from the other player. And different pieces they can be valued by different points. Again, there's some nuances here, but that's the main idea. Obviously, you in the end want to get to the king, but the main idea is that you want to take pieces from the other player, and different pieces have different values. The game of Go, on the other hand, it's a bit more complicated in the sense that what you want to do, and again I'm oversimplifying, is that you want to surround the other player's pieces. Which again, this is a bit of a more abstract thing to tell a computer how to do things. And this leads to also a more complex and broader game. So, how do computers do? Well, there's a whole documentary about this, it's out on YouTube and it's free, and you can watch it, and it's actually very interesting. But the main idea is that AlphaGo, the supercomputer, was able to beat Lee Sedol, who's was arguably the second best player in the world, 4-1. And this was quite a big deal, because basically AlphaGo, although Lee Sedol played impressively well, and he had some very incredible moves, particularly in the game that he won. I mean, on all of them, he's one of the best players in the world. But AlphaGo did dominate the games and beat Lee Sedol quite clearly. Then AlphaGo went to play with the number one player in the world, and it won actually 3-0. So again, just a very clear win from the part of the computer. Then they said, okay, if the best player cannot win versus the computer, how about getting the 5 best players in the world in a room and trying them to go against AlphaGo? And unfortunately, also all of them lost together versus AlphaGo, also without winning a single game. Now, a nuance here is that computers don't have a set strategy every time. So you can imagine that the computer doesn't play the same first move every single time. It's like playing rock, paper, scissors, right? So the computer will not simply do all the time rock or all the time scissors or all the time paper, because then what happens is that the opponent knows what to expect and can counter. So all of the games were somewhat random. So when two computers compete against each other, the game is also somewhat random. So it's not that you repeat the same game every single time. So what happened next is that they got AlphaGo Zero, a new computer, or a new computer that had even a different type of training, to play versus AlphaGo. And at this point, it was able to defeat in 100 different games AlphaGo. So it was 100-0. So by this point, obviously, there is no human player that can actually compete with well-trained machines. And the question here is, how did they manage it? And this was, of course, via reinforcement learning. So the actual way that this worked, and I'm going to go through many oversimplifications here. There's actually a research paper that you can read, which has all the information. But the main idea here is that you have, let's say, a snapshot of the board before it makes a move. So you have the snapshot of how the board looks, maybe even a few snapshots before, so that the computer knows what's the recent history of the game. And then the computer makes the move, decides what to move. So the way that these computers can be trained or were trained at some point is that you would first have what we call apprenticeship learning or behavioral cloning. And we'll be talking about it throughout the course as well, which was chess games or Go games when you have professional players that play this at tournaments, and these games are recorded. So what you could do is you could train in a supervised learning way. Again, there's nuances here, but you can train, let's say, in a supervised learning way, how the board configuration looked before an expert made a move and then after an expert made a move. And that would be basically the move that they made. So what you could do is you could scrape all these expert moves because they're obviously, again, there's record of these games. And in that way, your computer could have or could learn the behavior of the game that experts in the world played. And in that way, you could encapsulate the best players in the world's knowledge into a computer. This is a kind of Space Jam kind of approach. But not only that, not only is the computer able to encapsulate the knowledge of the best players in the world, but it's able to also do something that no human can do. And that is the idea of self-play. So what a computer can do now is it can also, once it has this very well trained, like pre-trained model, it can also play against itself, trying different strategies, seeing what works better, playing against itself. And in this way, it's obviously able to then perform much, much better than any human can ever do. And in this way was how AlphaGo was now able to beat every single player in the planet. Now, interestingly, and for our purposes, we're going to be looking at the techniques that were used here, but how they can be used in chemical engineering and in engineering in general. For things like, for example, controlling reactors, they're actually very similar techniques, or how to make decisions in supply chains. They're also reinforcement techniques, and we'll be looking at them throughout this course. So these are the three main types of machine learning. So again, supervised learning, where you give the labels, the correct answer, and this is practically a regression problem where you're trying to fit some kind of curve in many dimensions generally to the data that you have, or you're trying to fit a curve as well that separates different data. And again, this can generally be in very high dimensions, and this is where we're going to use many things like neural networks, Gaussian processes, and these other types of techniques. Then there is unsupervised learning, where, again, although all machine learning is some type of pattern recognition, but here you can think of it as giving lots of data and having some algorithm that find different patterns that we humans are not able to find. And then this is able to do things like anomaly detection in the case of chemical engineering. And finally, reinforcement learning, which is this idea of how to have a computer learn on its own to do some decision making or sequential decision making under uncertainty. And here it's where we can do things like optimizing systems, optimizing dynamic systems, modeling dynamic systems, and we'll be looking at this again throughout the course. So the first lecture will be on supervised learning, and it will be on linear regression, which is the simplest supervised learning technique. Again, we'll obviously be looking at more complicated supervising learning techniques, but we'll start with this one.